we have learned about intrinsic semiconductors and know that their conductivity is dependent on temperature. They have very low conductivity at room temperature, and thus no useful electronic device can be designed using these intrinsic semiconductors. To improve their conductivity, a small amount of suitable impurity is added to pure semiconductors like silicon. The semiconductors thus formed are known as extrinsic semiconductors. The process of adding this suitable impurity, say a few parts per million, to pure semiconductors is called doping. The suitable impurity that is added is known as a dopant. Now, the dopant must have the following properties. The dopant atom should be able to enter the structure of the semiconductor without distorting or changing the original lattice of the semiconductor in its pure state. So, these dopant atoms must be able to enter the structure of the semiconductor without distorting the shape too much. Second, the dopant atoms must not be too big or too small compared to the original atoms inside the semiconductor. There are two types of dopants that can be added to the tetravalent semiconductors like silicon and germanium, which can form two types of extrinsic semiconductors. We shall now understand the two types of semiconductors which are formed as a result of pentavalent and trivalent doping respectively, which create N-type semiconductors and P-type semiconductors. Pentavalent dopants which have a valency of 5, for example, arsenic, antimony and phosphorus, and trivalent impurities which have a valency of 3, for example, indium, boron and aluminum. We shall now understand the two types of semiconductors which are formed as a result of pentavalent and trivalent doping respectively, N-type semiconductors and P-type semiconductors. In N-type semiconductors, the doping is done using pentavalent impurities. As seen in the figure, when the tetravalent semiconductor like silicon or germanium is doped with a pentavalent atom, the dopant occupies the same position of the atom as the original atoms in the crystal structure. 4 electrons of the pentavalent atom bond with the 4 neighboring semiconductor atoms, but a 5th electron remains very weakly bound to the parent atom. This is an extra electron. Thus, the ionization energy required to set this 5th electron free is very, very low, and hence it becomes free to move inside the lattice of the semiconductor. Since the pentavalent impurity is donating 1 extra electron for conduction, it is known as a donor impurity. In an N-type semiconductor, the number of conduction electrons is equal to the electrons contributed by the donor plus those generated intrinsically inside the semiconductor minus the number of holes which came from the intrinsic source. However, the rate of the recombination of holes would increase due to increase in the number of electrons, resulting in further decrease in the number of holes. With proper doping, the number of conduction electrons can be made much larger than the number of holes. Thus, in an N-type extrinsic semiconductor, that is, having pentavalent impurity, the electrons are majority carriers and the holes are minority carriers. In N-type semiconductors, Ne is greater than Nh. For P-type semiconductors, which are formed by doping trivalent impurities into the structure, 3 electrons of the trivalent atom bond with the neighboring silicon or germanium atoms and offer a vacancy for the 4th atom. The bond between the 4th neighbor and the trivalent atom is a hole, a vacancy, an empty spot. Thus, an electron from the outer orbit of a neighboring semiconductor atom can jump to fill this vacancy, thus leaving a vacancy or hole in its own site. Thus, in the case of a trivalent impurity, holes or vacancies become available for conduction. Thus, it is known as an acceptor impurity. For a P-type semiconductor, the number of conducting holes is equal to those of the acceptor impurities plus those from the intrinsic source minus the number of electrons, which are those of the intrinsic semiconductor. Thus, in a P-type extrinsic semiconductor having trivalent impurity, holes are the majority carriers and electrons are the minority carriers. In a P-type semiconductor, Ne is much less than Nh. It is to be noted that extrinsic semiconductor crystals maintain an overall charge neutrality. The charge of the additional carriers is just equal and opposite to the ionized cores in the lattice. So, on the whole, the entire bulk of the semiconductor remains electrically neutral. Now, let's look at the electronic band structure or the energy band structure for extrinsic semiconductors. Let's see for n-type silicon. As we see in the figure, in an n-type silicon semiconductor, the donor energy level ED is slightly below the bottom EC. ED is the donor band, EC is the conduction band. A small supply of energy is sufficient for the electrons to move from the donor band ED to the conduction band EC. Thus, at room temperature, most of the donor atoms get ionized, whereas very few silicon atoms get ionized. For a p-type silicon semiconductor, as we see in the figure, the accepted energy level EA is slightly below the top EV or the valence band. A small supply of energy is sufficient for the electrons to move from EV to EA, from the valence band to the acceptor band. Alternatively, we can say that a small supply of energy is sufficient for the holes to sink from EA to EV, which means that at room temperature, most of the acceptor atoms get ionized, leaving holes in the valence band. The electron and hole concentration in a semiconductor in thermal equilibrium is given by the formula Ni square, that is the square of the total number of charge carriers, is equal to Ne times Nh. So let's summarize what we have done so far.
Manorama Horizon, learning made simple.